We're ready for Chapter 7, and Chapter 7 is where we get our second really big idea from the world of statistics. So we just finished talking about confidence intervals, which is kind of the first really big idea, and the second really big idea of this semester is the idea of what we call hypothesis tests, or some people call this inference. So we're going to do this section by section. I'm going to try to put it in a bunch of small videos so that you don't have to digest a 2-hour video at one time. But we'll combine these all together kind of into Chapter 7. So 7.1 is the elements of a test or hypothesis. So this is an overview, and I hope that by the end of this video you really have a picture of what we're thinking about when we say hypothesis test. First, let me just give you a little bit of an overview of things. So hypothesis test is really trying to get at this main idea of statistics that we've talked about all along. We have our sample and we have our population. And so what we have is we know some things about the sample. And so in the past, we knew X bar about the sample, and we tried to use that to guess what mu is from the population. Now what we're going to do is we're essentially going to turn this around and go backwards. And we're going to say, if we know mu from the population, what should the sample look like? This is really useful because if you think the way a lot of research happens is we're trying to detect differences between our sample and some sort of standard population number. So for example, if you're a doctor, you know that people might heal from a disease at a certain rate, and then you give them all a medication. You're trying to detect, did your medication in fact improve over what normally happens, or does it stay about the same as what normally happens? If you're a business and you have a certain amount of revenue that you know you can count on month after month, and you try something new in your business, you want to detect, did that something new make your sample different than what you expected, or is it behaving the exact same as expected? So whenever we start our hypothesis test, we're really going to always start in the same way. So we always start with our hypothesis or hypotheses. I should put an E in here. So our hypotheses are always going to have two parts. Our first hypothesis is going to be the null hypothesis, and our other hypothesis is going to be the alternative hypothesis. And we'll talk about this in pretty significant detail in the next video. But the big idea is the null hypothesis is the nothing happened hypothesis, and the alternative hypothesis is what you hope to find. Well, when I say hope to find, it's kind of what your research is trying to detect or not. And so if you're a doctor, then you're kind of hoping to find that you get lower, that people heal faster, or you have lower rates of sickness or something like that. The null hypothesis is that your medication, your experiment hasn't contributed anything at all. Now, what's important is when we come to hypothesis tests, it's really this null hypothesis is what we're starting with. So if I come back to my big picture, where we start is we start by making an assumption. And the assumption is our null hypothesis. So we always just assume that nothing is going on, and we'll kind of see why we want to make that assumption in just a minute. So once we have our null hypothesis, we find what's called our test statistic. And our test statistic is going to be a number that compares our data to a normal distribution. And I should probably say standard normal distribution, but we'll just say normal distribution. So what a test statistic does is it takes everything that we have in our data, so we've collected a bunch of information, and if H naught is true, then our possible results should follow a normal distribution, and our test statistic puts our results somewhere on that normal distribution. So let me come back over here. So we make an assumption, and then the next thing that happens is that assumption results in a normal distribution? Well, you might already guess. You might already guess that we are going to have cases where we have a t-distribution instead of a normal distribution, just kind of like last time. But let's just call them all normal for today. So that assumption results in some sort of normal distribution. So what we'll do is we'll place our data on that distribution. So maybe our data has some value like this. Maybe we'll come up with some number like that on our distribution. And that test statistic is our goal. That's what we're trying to do. We're trying to place our data at some point on that normal distribution. Okay. Well, once we've found our test statistic, our next thing to do is to find what we call a p-value. And our p-value is just an attempt to quantify how unlikely was our data. So it measures, so this finds the probability of our test statistic. Technically, or more, or worse, or more extreme. Because technically, when we find probabilities, we don't find probability of a single value, we find a probability of a range of values. And so the p-value is looking at our test statistic and saying, how likely is this? How much could this have happened just by chance? So if I come over here and look at my picture, then I've placed our data on the distribution, and the next thing I do is I ask, could this have happened by chance? And that's really the problem. That's really what we're asking. Could this data value have just happened by chance? And the way we do that is we find a probability, and that probability ends up being like a range on our normal distribution. So we have this normal distribution that came from our assumption. We put our z-value on that normal distribution, and now we're asking, what's the probability that that number could have showed up? And we get a p-value. So could this data value have just happened by chance, or does there have to be something unusual going on with our sample that makes our sample different from the rest of the population? Okay, so at this point, we now have what we call the level of significance. And the level of significance is just the point at which we determine our result was unlikely. It's traditional to use 0.05 or 5% as a level of significance, and that if something with less than a 5% chance happening occurs, then we kind of say, okay, that was pretty unlikely. It's a pretty unlikely point. But notice this is an arbitrary thing. There's not a science to figuring out this number. It just kind of depends upon your tolerance and your problem. So at this point, once we figure out whether our data value could have happened by chance, we now have two possibilities. Either our probability is very small, and if our probability is very small, then what we do is we say, no, it couldn't have happened by chance. And so if it's very small, then we say, then that means the most likely result, the reasonable conclusion is that our original assumption is false. So notice we started all this by making an assumption. Our assumption was that nothing interesting happened in our problem at all. So if we're talking about medicine, our assumption was that our medicine didn't do anything. So our assumption was that our medicine made no impact on our patients. If we then found what's the likelihood that our patients got better. So for example, you give a bunch of people medicine, they get better much faster than you would have expected. that means this probability would have been a really, really unlikely probability, that the chances of them getting better just by coincidence, by chance, is really, really, really small. And so if this probability is very small, then we say, well, we could have just gotten lucky and gotten like the 100 healthiest people in the world to take this medicine. But what's more likely is that the medicine actually made a difference, and that this assumption that we started with is a false assumption. Okay, so we come to one conclusion, and that is that H naught is false. But the other way is the probability is not very small. And if this is the case, it's tempting to say that that means that our assumption was true, but actually we can never say our assumption is true. Then all we do is we do not get a conclusion. Because it could be that your medicine is working, it's just working at such a small level that you weren't able to detect it with your test. It could be that your assumption is wrong, but it's wrong for some other reason than what you started with. So we never say our assumption's true. We actually only say our assumption is false. And this is kind of a big thing about our conclusion. Our conclusion only has one of two possibilities. Either we reject H naught, so that is either we say that our original assumption was false, or we fail to reject. Notice we never accept H naught. So when we come to quiz time, we come to test time, if you say accept H naught, then that's I'm going to be concerned about that. By the way, there are real scientists doing real science that get this wrong all the time when I read papers. I read a paper just this last spring that some of us were in a group together reading papers on academic research. And the person who wrote the paper, they did not get a very small p-value. They made an assumption, and then their probability was not very small. And so instead of saying we didn't draw a conclusion, they said, so therefore our original assumption was true. And I got mad, and I didn't get mad, but I ended up being a little bit upset, because I said this person doesn't understand how tests work. And it made me question everything else in their paper and the legitimacy of everything else in their paper, the fact that they didn't know this one fact about how tests work. So when you do a test, no, there's only two possibilities. Either you get a very small number and your H naught is false, or you don't get a very small number and there's no conclusion. H naught could be true, could be false. Our data doesn't make any commitment. Okay, this is just an overview. So we do this dance. It's really kind of a complicated dance. So the dance kind of looks like this. We start with the opposite of what we want to prove. Because we are only capable of showing that things are false, we kind of start with the opposite of what we want to prove, do a bunch of work, and find out how likely that opposite thing is. And if the opposite thing is really, really, really unlikely, then we say the opposite thing was probably false, and therefore what we're hoping to prove is probably true. It's a real unusual dance. It feels awkward mentally the first few times you go through it, but I hope that by the end of these videos, by the end of doing the homework, by the time the take-home quiz comes around, you will feel really confident on this. So enjoy the ride. It's really one of the big things that we do in statistics, and I hope that in about a week or two that this makes really good sense to you.